My name is Mike Kay from Lumen Dynamics, and we're going to talk today a little bit about UV spot curing for the assembly of medical devices. I thought we'd start, I'll give you just a quick background as to who we are as a company in Lumen Dynamics. We actually started as EFOS back in 1984, so we've been manufacturing UV spot curing systems for nearly 30 years. We were purchased by Expo back in 2001. And then just recently, October 2010, we were acquired by the Riverside company and changed our name to Lumen Dynamics. So we manufacture the Omnicure line of UV spot curing systems. We have offices globally. And at this point, we estimate we have probably about 15,000 UV spot curing systems in use in assembly processes globally. We offer both lamp and LED-based UV spot curing technology, and this is something we'll get into in quite a bit more detail throughout the presentation, really trying to look at the benefits of using either one of these technologies. Typical applications from a medical device standpoint include things like balloon catheters, ablation catheters, syringes, anesthesia masks, blood bags. There's many applications within medical device. Just a quick look at the products that we do offer for medical device manufacturing. Our lamp-based system is called the Omnicure 2000. So this uses a 200-watt mercury lamp. It includes a dichroic reflector, and what the dichroic reflector does is it basically eliminates the infrared energy from the lamp, so it allows for reduced heat when you're curing your parts together. It's got about 3,000 hour typical lifetime, and a peak irradiance of about 30 watts per square centimeter. Now you can adjust that output in 1% increments. And one of the real unique features we have within the Omnicure 2000 is what we call closed loop feedback technology. And what that does is with any arc lamp, it's going to degrade over time. So the closed loop feedback will automatically monitor the output from your system and then make any adjustments to the output in order to maintain a very steady irradiance level. So that allows you to have a very repeatable process because you know you're always going to have a very repeatable irradiance coming from the system. The system is automation friendly, so it can be run through an automated system or it can be run manually. And we also have 5 different filter selections available. And again, the filters can be used to further reduce the spectral content of the system. And that, again, can be very helpful in reducing the amount of heat. So if you have a very heat-sensitive process, you may want to use a specific filter, reduce the spectral content of the system. As far as the LED system goes, we have what's called the LX400 system. Now, LEDs, much longer lifetime, typical of about 20,000 hour from life. A peak irradiance of about 9.5 watts per square centimeter, although it is in a limited spot size, and so in this case, 9.5 watts is typically in about a 2 to 3 millimeter spot. With the system, you do have independent control of up to 4 different heads. You can again adjust the output in 1% increments. And something that we provided with our system is we have 3 different wavelengths available. So we have 365 nanometers, 385 nanometers, and 400 nanometers. And what you'll see as we go is this provides you with a little bit more flexibility in selecting the wavelength to match up to the adhesive that you want to use. So a little bit more flexibility by offering more wavelengths. We also have multiple lens systems or lens accessories that are available, which really allows you to maximize the output on your part depending on the spot size that you require and also the working distance of your process. Just recently launched, just launched at the show really, is the new Omnicure LED light meter, which now provides a radiometer for you to accurately measure the irradiance and power coming from your LED system in a radiometer that's been calibrated traceable to NIST. So we'll talk a little bit more about that as well. And finally, the third product we have that we see as being used for medical devices is what we call our LED light line. So in this system, instead of having a very small spot of light, you now have a 3-inch wide beam. Again, LED based, so it's 20,000 hour lifetime. Output is adjustable in 1% increments. This particular system is available 365 and 400 nanometers. It's got a nice high peak irradiance along this 3-inch wide beam. So it's ideal for conveyor type applications where you're moving parts underneath the light sources for small plastic parts, coatings, things like that. I thought before we went too much further, it'd be interesting to have a look at the current state of adoption of LED technology. Now, lamp technology has been around since our company started in 1984, very well established. LED is a much more recent technology. It's been around for about 10 years, although really only the last 5 years or so where it started to get to a level that it's really usable for spot curing systems. So if we look at the chart here, what we see is last year, about 40% of the UV spot curing systems sold globally were LED-based systems. So it's a pretty good adoption that has taken place over the last few years in really switching over to LED-based technology. However, if we look specifically at medical device assembly, we see it's really less than 10% adoption in medical device. And I find it interesting because LED is actually quite a nice fit for medical device manufacturing. It's very good at low temperature curing, which is ideal with assembly of plastic parts, such as we see in medical device. And it's also a very good fit for the free radical adhesives that are really very commonly used in medical device assembly. Certainly one of the things we're aware of is there's a very high cost in changing anything within a medical device assembly process. So there's a difficult justification to make to switch from a lamp to an LED, and we understand that that's part of the reason that is limiting the adoption. The other being the lack of an accurate radiometer, which is again something we think is being addressed recently with some new product lines. So really what we're seeing at this point is LED systems, in medical at least, really being purchased for R&D requirements, for testing, or for new processes. So at this point, we have the benefit of actually looking at other markets who've been using LEDs for a number of years now and have really made the transition quicker than medical. And we can look at some of perhaps the pitfalls that they've run into in making that transition and hopefully avoid those within the medical device. So it's actually, we're in a good position to look back over the last few years and really gain some advice from things that they have done. And certainly it's something that we are asked quite often at this point, is customers looking at transitioning from their lamps to their LED systems, and they want to know which one is going to work best for them. So what I thought we would do is moving forward, we'll have a look at the different systems, the different technologies, and we'll compare different features in each, and really hopefully give you a better idea of which technology may be better suited for your application. So things we'll look at are things like lamp life, environmental factors, something that's becoming much more important when you're establishing any assembly process. The curing factors, how well does each technology actually cure the adhesive? I mean, that's the bottom line when you're wanting to assemble your products. And radiometry. And we'll have a look and hopefully go through and give you a better idea of which technology may be best suited for you. So as I mentioned, when we look at lamp life, this curve here shows the typical lamp life of an arc-based, lamp-based system. It's got about a typical 3,000 hour lifetime, and you can see that the fastest degradation comes over the first 500 hours. So it loses about 20% of its total output in the first 500 hours. So it's not bad lifetime from the lamps, but not great. When you compare that to an LED system, you get a typical lifetime of 20,000 hours. Much longer. It's going to save you a lot of running costs when you establish a process. You're no longer having to replace your lamps on a 6-month or yearly basis. One thing I would like to point out, though, is that there's still about a 10% degradation in LEDs over the first 500 hours. Certainly one of the misconceptions we've seen over the previous years is people thinking that LEDs have no degradation over time, and that's just not the case. Really, depending on the system specifically, there is degradation. So it's still very important that you're monitoring the output of your LED system. When we look at now environmental factors, and UV curing is actually considered a green technology because the chemistry being used, there's lower solvent content, lower VOC content than other adhesive technologies. And it's also becoming more and more important for companies who are taking a stand to protect the environment with their assembly processes. So LED has definite advantages in environmental. LEDs are mercury-free versus the mercury arc lamps. They use about 80% less electrical power versus a lamp-based system, and there's no consumable items. So as far as environmentally goes, LEDs have a definite advantage. Now we're going to look at the actual light cure factors, or the factors of the UV spot curing system as it's going to cure the adhesive. So the 4 conditions which will affect the final cured properties of an adhesive are the exposure duration, the irradiance level, the spectral content, and heat. Now, the first three factors are things that can be directly controlled by the spot curing system. Heat is a byproduct of the reaction, but again, it's very important that the heat be managed within your process in order for you to have a successful assembly of your parts. And it is important because we have seen many times through our testing that the same adhesive, if you use a different curing process, if you use a different irradiance level, you can actually get different physical properties from that adhesive, different bond strength, different moisture resistance or flexibility. So it's important that you establish a process where you understand these different factors and then you maintain them in order to maintain a very repeatable process. So first thing, if we look at irradiance power from a system, lamps have a very definite advantage here over the LEDs. A lamp system, you get about 30 watts per square centimeter versus an LED where it's about 9.5. The lamps, you can cover a spot about 10 to 12 millimeters in diameter versus an LED system, you're limited to about 4 millimeter spot sizes. One of the areas where LEDs sort of mitigate this advantage is if you're using multiple cure sites. With an LED system, you're using multiple heads. Each head will still maintain that maximum of 9.5 watts per square centimeter. With a lamp system, to get multiple cure sites, you're adding legs to your light guide. And as you add legs, you reduce the total output from each leg as you add them. So there's one area where the LEDs do have a bit of an advantage. Next, we're going to look at spectral output. So this chart here shows you the spectral output of both a lamp system here, very broad band, goes from about 250 to 500 nanometers, versus an LED spectral output here, in this case our 365 nanometer output. So it's clear it's a very broad lamp base versus a narrow spectrum of an LED. The LED is typically about 10 to 15 nanometers, but which is better is the question. And the answer is really each has an advantage in different areas. If we look at the actual curing requirements, in order to cure adhesive, the adhesive must receive sufficient light of the correct wavelength in order to start the photoinitiator reaction, in order to cure the adhesive. So when you look at the narrow spectral band of the LED, you realize that it's now critical that you match that spectral output of the LED with the absorption spectra of the photoinitiator within your adhesive. If you don't match those two up, you're not going to get any curing, regardless of the irradiance level. That's one of the reasons with our LED system we offer 3 different wavelengths. It makes it a little bit easier to match the wavelength of the LED to the requirements of the adhesive. However, when you compare that to the broadband of the lamp, you can see that it's much easier for a lamp system to be compatible with the adhesive that you're using because it's going to cover the entire spectrum of the photoinitiator. However, the other aspect of the spectral content is heat. So light beyond that is needed for the photoinitiator is now absorbed by the adhesive, and that generates heat. You also get light that's absorbed by the materials that are being joined, and again, that's going to generate heat. So although with lamp-based systems you can use filters to reduce the spectral content, what you're going to find is that with an LED system and the narrow band of an LED, you're going to get much lower heat. The chart here gives an example of a process where we actually measure the temperature using various curing technologies. So the blue line here is 2 parts joined together with a lamp-based system with no filter. And you can see it reached a maximum of about 53 degrees Celsius. We threw in a 320 to 500 nanometer filter, reduced the spectral content, and we were able to reduce the heat down to 40 degrees. So it's a pretty significant reduction. But down here, when you use an LED system, in this case a 365 nanometer LED system, you're able to reduce the heat down to about 3.5 degrees Celsius. So much better management of the heat with using LED. So a big advantage to LED. Now, again, with our system, you have 3 different wavelengths to choose, 365, 385, and 400 nanometers. So which one is best for your process? Many adhesives will specify 365 nanometer light, and that's traditionally they've been designed to match up with the 365 nanometer peak of mercury lamps. What we find in our testing, though, is many free radical formulations will cure quite well with wavelengths up to 420 nanometers. Cationics, they tend to cut off a bit lower, up to about 380 nanometers can cure them quite well. And in general, using a 400 nanometer will actually give you a better through cure than a 365. whereas a 365 nanometer LED tends to give you a bit better surface cure than your 400 nanometer. And finally, you can't forget the substrate that you're joining as part of your decision-making process on which wavelength is best suited. This here, it gives you an example of some testing that we did, joining two plastic parts, using adhesive where it specified 365 nanometer wavelength to cure the adhesive. But when we actually went and tested the transmission of light through the plastics, we found that at 365 nanometers, the parts being cured were actually absorbing about 50% of the 365 nanometer energy. So only half the energy was actually getting to the adhesive. Whereas at 400 nanometers, you're now getting about 80% transmission of the light. So you're getting much higher energy through the parts to the adhesive at 400 nanometers. And what we actually found is that at 400 nanometers, the adhesive cured faster and with less heat as compared to the 365. So in this case, if you had followed the specs of the adhesive exactly, you probably wouldn't have had the most efficient process for assembly. The other thing to look at with adhesive compatibility, and again, this is a really important point that we get asked all the time, is many adhesives have been designed to work with broad spectrum of lamp-based systems. Many of them will have multiple photoinitiators, varied absorption peaks, and again, that was to take advantage of the broad spectrum of the lamp systems. So if you now want to move your process from a broad spectrum of a lamp to the very narrow spectrum of the LED, will you get the same curing? And it's a really important question to ask, because if you don't get the same curing, then obviously you need to know that as part of your testing. So I wanted to share with you some of the testing that we've done along those lines to really try and identify whether taking a process that you know works with a lamp system, transitioning it to an LED, and see whether or not you're going to get the same results. So the chart here shows results of what we measured here, and in this case it's microhardness. Now we use microhardness as an indicator on whether or not an adhesive is cured. It's not an exact confirmation that the adhesive is fully cured, but what you do is if you cure an adhesive to the point where you know it's cured, you measure the microhardness. This now gives you a baseline, so as you're doing further testing, you know that if you reach that same microhardness, it's at least an indicator that your adhesive is fully cured. So in this case, we took an adhesive that we knew if we cured it with the lamp, we would get it fully cured, and we reached a microhardness of right around 60. Took the same adhesive, replaced our lamp with an LED system, in this case, a 365 nanometer LED system, and we achieved a microhardness even a little bit better. So based on this, it would at least indicate that the LED system did cure the adhesive at least equally as well as the lamp system. However, when we took those same samples and did really a more direct analytical testing with them, in this case we looked at them, we looked at it at a DSC system, where we could actually show the amount of uncured material within those samples. What we found is this line here, the blue line, shows the sample that was cured by the lamp-based system versus the red line, which was the sample cured by the LED. So, in fact, although both samples achieved the same microhardness level, there was significantly more uncured material within the adhesive that was cured by the LED. So based on this further testing, you would have to say that no, these adhesives were not cured equally well with both lamp and LED. Now this is just one example of one adhesive, but I think it's really important to make this distinction that curing with an LED is very different than curing with a lamp-based system, so it's very important that you follow through on the testing, on the analysis, to ensure that you are getting the same cured properties with either of the technologies. So finally, we'll talk a little bit about the radiometry. Again, lamp systems have been around for years. The radiometry is very well established. There's a number of radiometers out there that work very well for measuring the output from your lamp-based systems. So although LEDs we saw degrade much slower than lamp-based systems, they do still degrade, and it's still very important that you're monitoring and measuring the output from your system. The challenge with LEDs is that unlike the lamps, one, they're a very narrow spectrum, but two, it's also very narrow beam patterns, and both of these present challenges for radiometers. So we've actually introduced the new Omnicure LED light meter which we think has really tackled both of these challenges in a very unique product. What we've done is we have a very special calibration process where we actually calibrate the sensor at 10 nanometer intervals from 300 nanometers up to 720 nanometers. What this allows you to do is you can actually now select the specific wavelength that you're using to match up with your LED system and measure the output at that specific wavelength, knowing that your radiometer has been calibrated traceable to NIST at that wavelength. So we think it's a pretty unique product that, again, will be very helpful for medical device manufacturers who need radiometry to measure and maintain the output for their systems. So if we go back and really summarize the different features that we looked at in the lamps and the LED systems, and we compare which one has the advantages, what we see is the LED certainly has advantages in things like lifetime, environmental, the electrical power requirements, again, advantage to LED. But things like the picoradians, spot size, lamp still has a definite advantage there. As far as the spectrum goes, you have the broad spectrum of the lamp versus the narrow of the LED, and each one has their own advantages. Certainly LED has the advantage of lower heat, where the lamp system really has the advantage of better compatibility with adhesives. Although I must say that more and more adhesives are being designed specifically to work with LED curing systems. And so there's a different set of photoinitiators being used, a different chemistry. And so as we move ahead, there's definitely going to be much better compatibility of the adhesives with the LED systems as they go. The formulas are getting better working with the LED systems. And then finally, radiometry in the lamp system is much better established versus the LED, where it's really still being developed and perfected. So based on this, which system is best for you? And well, the answer to that is, unfortunately, the answer to that really is going to depend upon your process, the parts you're joining, your application, and really what works for you. I think the key, though, is to really understand the different benefits that each one brings and really help you to use the best technology for your process. And for that, we'd be happy to work with you and help you out, because we do have both technologies available. So by all means, come visit us at booth 2227. And that's the end of the presentation. So if there's any questions, please, I guess, step up to the mic, and I'm happy to answer any questions.
Are there any advantages with residual stress and lower shrinkage with LED because of the lower temperatures?
The lower temperatures definitely helps with the lower stress and the lower shrinkage. Although again, it's something you can manage with a lamp-based system. Was that you? Okay. But again, it's an area that an LED would inherently have a bit of an advantage because you're going to have lower heat. Yep. All right. Thank you very much, and enjoy the rest of the show.